So today in lecture 2H, we're going to talk about a series of molecules known as hydrocarbons. And as the name might suggest, these are molecules that are composed of two different elements. They're composed of carbon and hydrogen. And carbon and hydrogen can form lots and lots of different molecules. So there's actually a systematic way to name these. We're going to talk about naming some simple hydrocarbons today. Now, the reason there are so many molecules that exist made of carbon and hydrogen is that carbon atoms can bond together in long chains. 2 carbon atoms can bond together, 3 can bond together, 4, 5, 6, 20, 50, 90, 100. And when these carbons bond, if the carbon atoms all bond with single bonds, then these hydrocarbons are called saturated hydrocarbons. So these would be hydrocarbons, once again, compounds made of only carbon and hydrogen, that only have single bonds between the carbon atoms. If that's the case, we call them saturated, and we'll try to explain why they use the word saturated in a little bit. So if you have a compound made of only carbons and hydrogens, and you want to name that, what they do is they actually have a little prefix that tells how many carbons are in the longest chain of the molecule. So there's a prefix that tells the number of carbon atoms that exist in your particular hydrocarbon molecule. And specifically, this means the number of carbon atoms in the longest chain. So if you have one carbon only in the molecule, we use the prefix meth. If you have 2 carbons in a chain, we use eth. 3 carbons in a chain is prop. 4 is bute. 5 is pent. That pent is the first one here that sort of sounds familiar, penta meaning for 5. And then if the numbers go higher than this, you'll recognize these. 6 is hex, 7 is hept, 8 is oct, 9 is non, 10 would be dec. And they actually go higher than this, but this will suffice. So if you have a hydrocarbon and you know how many carbons are in the longest chain, you pick the appropriate prefix that you see here. And then what's the suffix? What do you put at the end? You put the ending ANE. That ANE ending indicates that there's only single bonds between all the carbons in the chain, okay? So if you had a hydrocarbon that only had 1 carbon in it, what is its name?
Methane.
Right, and we learned that, right? Methane is, what's its formula? CH4, that's 1 carbon. So that's a hydrocarbon that only has 1 carbon in it. It's called methane because that's its systematic name that organic chemists have given to it. Organic chemistry, once again, being the chemistry of carbon compounds. So you wind up taking organic chemistry in a year from now, and the first thing you're going to learn is how do you name hydrocarbon compounds. I remember going to organic chemistry, and over the summer, I thought it was going to be so hot, and I read the first 50 pages of the textbook before the semester started, and I went in there on the first day, and we covered the first 50 pages on the first day, and I was behind already. I go, wow, this is going to go fast, and it kind of does. So methane would be the simplest hydrocarbon because meth means 1 carbon, and methane means only carbons and hydrogens. And so it turns out the formula for methane is CH4. So we're going to use methane as an example of the things I will expect you to be able to represent about molecules on your test too. So here we go. What would I ask you about methane? I would say, what's the Lewis structure? You would have to go, oh, these are both nonmetals, so they bond covalently, as opposed to a metal and a nonmetal, which would bond ionically. So if you were going to draw the Lewis structure of an ionic compound, you draw a separate positive ion and a separate negative ion. Because these are nonmetals, they bond covalently, so you got to hook them together with dashes because dashes represent shared pairs of electrons. So you would add up 4 plus 1 plus 1 plus 1 plus 1, 8 total electrons. Draw a skeletal structure that's showing the carbon and the hydrogen sharing electrons, and those dashes mean sharing electrons. And then you would add all the rest of the electrons in as lone pairs, but this structure I've drawn here already has the 8 valence electrons. I'm done. You verify that all the atoms have noble gas configurations, duets for hydrogen, octets for carbon. And if a central atom could exceed the octet rule, you'd want to check the formal charge because maybe you should draw a better structure, but there's no atom here that can exceed the octet rule, so this must be the correct Lewis representation for methane, okay? Now, just like on our last homework assignment, I will ask you, what kind of hybridization do you think the carbon is undergoing to make this molecule? And the way you answer that is you determine carbon's steric number. And because the steric number of carbon is 4, you count on your fingers S, PX, PY, PZ. What did I use? 1 S and 3 Ps. Therefore, the hybridization of carbon has to be sp3 to form this molecule. Okay? I will say, what shape do you think the molecule is? And that really comes just from the steric number. If you have a steric number 4 and they're all atoms bonded to the carbon, the shape of that molecule is a tetrahedron. And that'll be a tetrahedron because the sp3 orbitals all point to the 4 corners of a tetrahedron. This is the correspondence you have to understand. If you know sp3 hybridization comes from a steric number of 4, that's telling you that the sp3 orbitals have to be pointing in a tetrahedron because that's the shape of a steric number of 4. So these 4 sp3 hybrid orbitals then, when they bond to 4 hydrogens, would wind up making a molecule that has a tetrahedral shape. You create 4 bonds here, and you have a tetrahedrally shaped molecule. Now, I'm going to want you to be able to draw a picture of this molecule, but I don't want these big bloopy purple, red, orange, yellow pictures like this. That's going to be hard to do unless you're a master artist. So I want you to draw it in stick figures, much like we talked about earlier. How do you draw a tetrahedron? You draw 2 lines that are flat on the paper, 109-degree angle. Then because a tetrahedron, in this case, the orange bond is coming towards you, you draw that bond as a wedge. And the yellow bond is going back behind the plane of the paper, you draw that as a receding dotted line. So I would want you to be able to represent to the best of your ability the physical appearance of this methane molecule by using lines as bonds, and they're straight lines if the bonds are flat on the paper. It's a wedge if the bond's coming out towards you. It's a dotted line if the bond is going back behind the plane of the paper. So the shape of this molecule is tetrahedral. Next, I would like you to be able to tell me if this molecule is polar or not. So you're going to have to look up electronegativities. There'll be instances where I will not tell you electronegativity, so I'll expect you to look in the periodic table where the positions of the elements are and predict if you think the elements would have different electronegativities and which one would be higher. Based upon their positions on the periodic table, which element do you think would have the higher electronegativity, carbon or hydrogen? Yeah, it's further to the right. So these are polar bonds. The dipole moment arrows would all point towards the carbon. Doesn't matter if they point in or out. In this case, they all point in. But how are those 4 dipole moments arranged? In a tetrahedron. That's one of the 4 symmetrical arrangements. So the 4 dipole moments I probably should have drawn on this picture, which are all pointing to the carbon, I would then erase them all, and I wind up having a molecule with no dipole moments left, so therefore it's nonpolar. The final thing I'm going to ask you is what's the name of each of the bonds in the molecule? And because whenever you form a bond, orbitals overlap with each other and they become symmetrical around the internuclear axis, these are always called sigma bonds. Now, you just have to name the 2 atomic orbitals that created them. So you have to know the name of what this orbital was before it merged and what this orbital was before it merged. This was a 1s orbital on the hydrogen. This was an sp3 orbital on the carbon, and now they merge together to form the bond that's called sigma, sp3 plus 1s. All right? I would say a large chunk of the test will be me giving you a number of molecules and you answering every single one of these questions about those molecules. Okay?
Professor, just to recap, we have to know and draw the shape, but not the orbitals.
Correct. So what's in white up there, the big picture in white, I will not expect you to draw. I think that's a little bit pushing it. But the stick figure picture at the bottom, absolutely.
Okay, thank you.
Okay. So if you see something whose name is ethane, the F means 2 carbons. The ane means single bonds between the carbons. So this would be a molecule that has 2 carbons bonded in a row with a single bond between them, and then a bunch of hydrogens attached to it. Turns out the formula for ethane is C2H6. Let's see if we can actually draw the structure for this. The number of valence electrons would be 4 plus 4 is 8, plus 6 more, there'd be 14. So the skeletal structure for a hydrocarbon is the carbons bond in a chain. You attach the 2 carbons to each other, and then the 6 hydrogens have to bond to those carbons. And if you go ahead, yes, questions.
Sorry for interrupting, but how come that's not CH3?
if you try to draw the Lewis structure for CH3, you will not get an octet for the carbon.
Right.
So
Okay.
that's not a correct molecule. So you're thinking about, I think I want to write this as an empirical formula. If you remember what a molecular formula is, it's telling you the actual number of atoms that are bonding together to make the molecule in order actually for each of them to achieve noble gas configurations. So its empirical formula is CH3. I 100% agree. But there is no such entity, no such molecule as CH3 because there aren't enough electrons to allow carbon to have an octet, so that substance would never be stable. But if a pair of CH3s hook together, now it turns out all the atoms can make octets. This is a stable substance, and so what we give you here is its molecular formula, the actual number of atoms bonding in the unit, the molecule itself.
Great, thank you.
So if this is the actual number of atoms bonding together, you have to show them all in your structure, and the carbons have to go in a chain, so you attach the two carbons to each other. And if you think about how carbons need to have octet configurations, then the 6 hydrogens have to have 3 bonded to one carbon and 3 bonded to the other. You can't bond 4 hydrogens to the first carbon and 2 hydrogens to the next. One would exceed the octet rule and one wouldn't have the octet rule. So there really is no other choice. So attach 3 hydrogens to each carbon. That's your skeletal structure. It happens to use 14 electrons. We're done. No atom can exceed the octet rule. So this is the perfect structure. The carbons have octets and the hydrogens each have duets. Let's see if we can answer the same question for this molecule. If I ask you what's the hybridization of each of the carbons, what do you think it's going to be?
sp3.
That's because each carbon has a steric number of 4, right? And so you hybridize an S, a PX, a PY, and a PZ for each of them. So each carbon, because they have steric numbers of 4, will be sp3 hybridized, okay? Now, what does that molecule look like, okay? Well, let me draw the first carbon here. It has 4 different sp3 orbitals, and how are those sp3 orbitals arranged in space? And this is actually on, I think, which handout is that? I think it's handout 4, and it's on like the 2nd or 3rd page where I actually show you the arrangements of all of the different hybridized orbitals. So you'll need to be familiar with those. You need to know that sp3 orbitals point in a tetrahedron. So these are going to be the orbitals that are going to bond to the hydrogens and the carbon. So if this first carbon is going to bond to a second carbon, the second carbon's either going to bond to the purple orbital or the yellow orbital or the orange orbital or the red orbital. I'm going to bond it to the red orbital if that's okay. So I'm going to draw my second carbon down here so I can line up an orbital on the second carbon with an orbital on this carbon. And the second carbon has the exact same hybridization, so I have to draw its orbitals in a tetrahedral shape as well. Now, watch how I draw it. That look a little bit different. What did I do? I rotated it. Why did I rotate it to the left? How come I didn't draw the purple orbital straight up and down like I drew this one? Why would
Because
that
the carbon atom has to bond to the other carbon atom.
And the only way the atoms can bond is if orbitals overlap with each other, which means they have to point at each other. So I have this red orbital here that's going to make a bond with a carbon. I need an orbital here that's going to be pointing at it. So when these approach each other, there's your bond. Does that make sense? So as you're putting molecules together, you're going to have to be cognizant of the fact that if 2 atoms are going to come together to bond, you better have an orbital on each of those atoms pointing at each other, okay? So sometimes that's going to mean you rotate around your little tetrahedral picture. If we see how the hydrogens are going to bond now, the hydrogens can bond to the 3 remaining sp3 orbitals on both of those carbons, and you can see they just come and go, boom, just like that. That's what the molecule is going to look like, but you're not going to be drawing that picture. You're going to be drawing a stick figure picture. So watch how I have to do essentially the same thing, but with stick figures instead. Let me start with the first carbon, the top one there. We know it has a steric number of 4, so it's sp3 hybridized. Those orbitals are tetrahedral. So I'm going to draw my carbon as a tetrahedron. So look at that, 2 lines flat on the paper, 109 degrees apart from each other. The bond coming out towards you is a wedge. Going back behind you is a dotted line. And I know 3 hydrogens are going to bond to those. Okay. When I draw my second carbon, I'm not going to draw it exactly the same with a hydrogen pointing straight up, because if I do that, I won't have orbitals that are pointing at each other. So I'm going to take this tetrahedral array and I'm going to rotate it slightly to the left. So watch this, rotate it like that. And I'm going to use the top bond to be the one that overlaps with the empty orbital on the first carbon. So they can create a bond between the two carbons. So if you want to see the tetrahedron, you have to turn your head 109.5 degrees to the left. And then my right carbon will exactly look like a tetrahedron, just like the left carbon is. It's just rotated 109.5 degrees. That's really important that you can see that, okay, and see why we did that. It's because you need the orbitals pointing at each other to bond. So the second carbon rotates over and then attaches to the first, and we wind up having a bond between the two carbons like this, and the three hydrogens wind up taking the positions in the final three sp3 orbitals. So what I'm going to do when I grade yours is I'm going to look at your first carbon. I'm going to go, is that a perfect tetrahedron? Ah, nice job. Then I'm going to look at the second carbon and I'm going to take your test and I'm going to rotate it 109.5 degrees. And I'm going to see, does that look like a tetrahedron also? And if it does, 100%. Okay. Can you see how that stick figure is representing what you see in the white box above? Everything okay with that?
I'm a little confused, Professor, because I would have thought that the two hydrogens that you have on the second bonded carbon would have been flipped.
Oh, you can flip those if you want. You can put a wedge here and a dotted line there, and that would be perfectly fine.
Okay.
It's like these two can be flipped here. You can put a wedge here and a dotted line there if you'd like. It just, when I think artistically, the one that's coming out to you always looks like it's closer. So I like putting that first, and the one going behind always seems like it should go behind to me, but you could do it the other way around. And for these two, I actually think this is the one that's coming out towards me. So that really should be the wedge. That does look right. This is going back behind. So I put the dotted line like that. But if you flip those two, if that's what you're saying, it would actually be the same thing. That would not be a problem.
I think it's just easier for me to visualize. So that's the only reason.
Yeah. If you want to do, are you right-handed?
Yes.
Yeah, that's probably why. I'm left-handed, so I like it this way. I'm just kidding. Okay, so now let's name each of the bonds in that molecule, okay? What's the name of the bond between the two carbon atoms? Up here in this picture at the top, it's the overlap of the red and the purple orbitals. What's the name of that bond?
Pi bond?
It's not. It's a bond where the two orbitals have overlapped. So if you draw the inner nuclear axis here and you spin this around, it still looks perfectly symmetrical. So that's still a sigma bond. Definition of a sigma bond is if you draw an inner nuclear axis and imagine the bond rotating around like on a skewer. If it always looks the same, that's not a pi bond. That's a sigma bond. So there's still sigma. So what do you put in the parentheses after the sigma?
You would put 2 sp3?
So the way we would write that is we write sp3 plus sp3.
Okay.
So what are you overlapping? An sp3 orbital on the first carbon with an sp3 orbital on the second carbon. So that's written sigma sp3 plus sp3. Every single bond we've done up till now, we've always added something like a sp3 plus a 1s because we're always bonding with hydrogens, and hydrogens have their electron in a 1s orbital. But here's the first case where you'll see that's not always true. You just have to name the two orbitals that are overlapping together to make the bond. So in this case, it's a pair of sp3 orbitals that are overlapping. So that bond is a sigma sp3 plus sp3. Okay. What's the name of each of the bonds here between the carbon and the hydrogen, this carbon and hydrogen, this carbon and hydrogen, and the same for this, same for this, same for this? What are the name of those carbon-hydrogen bonds?
Those are sp3 plus 1s.
Right, so those are the overlap of the sp3 orbital from the carbon with the 1s orbital from the hydrogen. So each of those bonds are named sigma sp3 plus 1s. Now all the bonds are labeled in the compound, okay? Now, an interesting fact about hydrocarbons. When we analyzed methane for its polarity a few minutes ago, methane turned out to be a non-polar molecule because you had 4 dipole moments in a tetrahedron. I want you to look at this molecule down here on the bottom left, okay? What kind of dipole moment arrow do I draw in my carbon-carbon bond here?
You don't have one?
Oh my goodness, who said that?
I did.
Is that Mr. Holmes?
It's Shiner.
Oh, Excellent job. So that's because these two atoms are the same element. They have the same electronegativity. If they have the same electronegativity, there's no difference. So if you have bonds between atoms of the same element, you do not draw a dipole moment arrow. Perfect. Now, these have dipole moment arrows because there's difference in electronegativities of the carbons and hydrogens. So a dipole moment pointing towards the carbon here, dipole moment here, dipole moment there. That is not one of the symmetrical arrangements we learned, correct? So you wouldn't be canceling those out. But look on the other side. Dipole moment here, dipole moment here, dipole moment here. Can you see how the three dipole moments on the right side are related to the three dipole moments on the left side? What do you see? How are they related to each other?
Cancel each other.
They're equal but opposite. That means they'll cancel out. That means C2H6 is nonpolar as well. And if we were to do C3H8 or C4H10 or C5H12, guess what? You're always going to have dipole moments that are exactly equal but opposite on either end of the molecule that are cancel out. So it turns out that hydrocarbons are always non-polar. If you go into the organic chemistry classroom next time you're at school and walk in there and you say C5H12, is that polar or non-polar? No student in organic chemistry is going to draw the Lewis structure, draw out the molecule, draw all the dipole moments in there and figure out if they cancel out or not. They'll go, oh, it's non-polar because it's a hydrocarbon, because they learned back in general chemistry that anytime you have to C's and H's, because of the symmetry of the molecules, the three dipole moments here would cancel out with the three dipole moments here, and that would be the same even if the molecule is really, really long. So as we progress throughout this course, I will be referring occasionally to the polarity of hydrocarbons, and I'm not going to draw them out necessarily anymore. I'm going to go, oh, they're just always non-polar. That'll be actually a good thing to know. Okay?
So every hydrocarbon is nonpolar?
Yes. Now, remember, hydrocarbon means only carbon and hydrogen. So if you have a compound that's C3H8 and then it has O in it, that's not a hydrocarbon anymore. That's something different. But it's only carbons and hydrogens. Always non-polar, yes.
Okay, thank you.
Now, those were examples of what we called saturated hydrocarbons. What's an unsaturated hydrocarbon? These are hydrocarbons that have at least one double or triple bond between the carbon atoms. And the way we name an unsaturated hydrocarbon is with the same prefix as we talked about before, but we have a different ending. The suffix ane means only single bonds. But if you have a double bond between at least two of the carbons, we switch the ending to ene. So that indicates a double bond between carbons. And the way a double bond forms is significantly different than anything else we've seen in this unit up until now. A double bond consists of two bonds. One of them will be a sigma bond, much like we've seen so far today. But the second bond in a double bond is always something called a pi bond. So double bonds always consist of a sigma bond and a pi bond, whereas you wrote down in your definition earlier today, a pi bond is a bond that is only symmetrical if you rotate it 180 degrees. Sigma bond, remember, was symmetrical if you rotated any number of degrees, 3, 37, 142. It always looks the same. It's like a football. You skewer a football, you rotate it around any number of degrees, it always looks the same. But a pi bond, that's not the case for. The pi bond only looks exactly the same if you rotate it 180 degrees. And we're going to see bonds like this in any molecules that have double bonding in them. So let's look at the simplest unsaturated hydrocarbon. Because you need to have a double bond between two carbons, there are no unsaturated hydrocarbons with only one carbon, so there isn't any methane. You have to have at least two carbons, so the simplest unsaturated hydrocarbon is called ethene. And ethene's formula, as it turns out, is C2H4. Now, if we want to draw the Lewis structure for ethene, we'll add up the valence electrons. 4 and 4, oh my goodness, I think I wrote the wrong number on here. That's a shame. But carbons are 4 and 4, that adds up to 8. And then the hydrogens, 4 more would be 12. So look at that, that says 10 there. So we're going to fix that. I don't want that, that's bad. Quality control. Okay, try again. So ethene has 12 valence electrons. The skeletal structure will bond the two carbons together, And then the 4 hydrogens have to be bonded to those. And so if you have a symmetrical molecule like this, C2H4, I would put 2 hydrogens on one carbon, 2 hydrogens on the other. If you wind up not doing that, you won't be able to make octets. So you'll quickly learn that would be wrong.
Professor, just a quick question. Was
Sure.
that it? Ethane or ethane?
Ethane. Ethane. The first, what we had before, C2H6 was ethane, A-N-E. This is ethene. The ENE ending pronounced with a long E, ethene.
Thank you.
And what the difference is, ENE ending means there must be a double bond. So let's figure out where the double bond is and how you do that. Now, if you're going to draw the Lewis structure for a molecule, you would add up the 12 valence electrons, put in all the bonds. That's 2, 4, 6, 8, 10. We need 2 more electrons. How do you always put the electrons in? As a lone pair. So you put the lone pair on an atom that would make an octet. So the hydrogens have duets. The carbon has an octet there, but the other carbon, curses, only has 6 electrons in its outer shell. So that means this is not wrong. So what do you do with that lone pair?
Double bond.
Move it into a sharing position and make a double bond. Up, there you go. Now you have octets for both carbons. That's ethene. Okay. What's the hybridization of each of the carbons here in the ethene molecule?
sp2.
Yes, it is, because their steric numbers are 3. They're only bonding to 3 atoms. You hybridize 3 orbitals, an s, a px, and a py, and you end it. So they're sp2 hybridized. What's the geometry of sp2 hybridized orbitals?
Trigonal planar.
Perfect. And here's what's going to really be important. Because we did not hybridize the pz orbital, I need you to be able to show me where that pz orbital is in relationship to the trigonal planar sp2s. So this is really important. The sp2s are forming a trigonal planar geometry, kind of like the equator on the Earth here, right? Here's the Earth. The purple orbital is the North and South Pole, and this is the equator. So I've drawn these 120 degrees, 120 degrees, 120 degrees, making a perfect triangle around the equator. Those are the sp2 orbitals. The unhybridized pz orbital is perpendicular to that, pointing straight up and down. Okay? What the carbon does is it puts its 4 electrons, 1 in the red orbital, 1 in the orange, 1 in the yellow, and 1 in the purple. So this red orbital right here will be able to overlap with an orbital on another atom coming from the right side, and that's going to be the other carbon atom. The other carbon atom is also sp2, so I'm going to draw its orbitals here, but I'm going to have to draw those orbitals so that I can have an orbital on each atom facing each other to overlap. So I'm not going to draw it exactly the same. I'm going to spin it around like this. So can you see why that's spun around? Because if you want to bond with this orbital, you need an orbital over here pointing directly at it. And whenever orbitals point at each other and they overlap, they always form sigma bonds because their overlap is perfectly symmetrical. Okay? So the way these 2 carbon atoms are going to bond is they're going to come together, and the red sp2 orbitals are going to overlap, and that's going to form a bond. What's this bond right here called?
sp2 plus sp2.
Perfect. It's sigma sp2 plus sp2. Excellent. That's one of the 2 bonds. Somehow there has to be a second bond between the 2 atoms. Now you see the yellow and orange orbitals here pointing way back in the opposite direction? Those are going to bond to these hydrogens. See the yellow and orange orbitals here pointing off in the opposite direction? They're going to bond to the hydrogens. What orbitals do you think are making the second bond in the molecule?
Pi bond.
What orbitals are making the second bond? So a pi bond is an orbital. What orbitals are going to make that second bond?
sp2 plus 1s.
So there's no 1s orbital anywhere here. The 2 carbon atoms only have, if we go back, sp2, 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 and then 2pz. So don't pick 1s, that doesn't exist, okay? So as they bond together, it either has to be the purple, the orange, or the yellow. So you want to name to me which one of those orbitals do you think is going to bond with which orbital on this atom over here to make the second bond?
The 2pz.
Probably, because this sp2 is pointing off in the right direction. This one's pointing off in the left. They can't bond with each other, but maybe these guys can. Now, the problem is they're not pointing at each other, right? It doesn't look like they're going to actually bond. Well, there's a different type of bond that can be formed for that do point at each other if the orbitals are parallel to each other. You see the inner edge of this p orbital here up at the top? The inner edge here, they actually get close enough to overlap. What I have done is I've been very kind to my p orbitals. I have really thinned them out, did some Photoshop work on them, make them look really good. But those p orbitals are actually much bigger than I've shown here. It's just if I draw them really big, that makes the picture really hard to see. So if this p orbital is really big, and it's really big for this one, then the insides will slightly overlap above the sigma bond here. And the same thing happens on the bottom. This lobe is actually really much wider. This lobe is much wider. So they're going to overlap a little bit below the sigma bond. And so when you have orbitals that are parallel to each other, and in this case, the 2pz and the 2pz are parallel, they're going to slightly overlap on the top and the bottom. So we have one bond between the carbons, which we've already identified. The red overlap is called the sigma sp2 plus sp2. But now we're going to have these p orbitals overlap a little bit above the sigma bond and a little bit below the sigma bond. And those two overlaps combine to make the second bond. Now, here's the internuclear axis, okay? What does this bond look like? It looks like a big square. I want you to imagine you actually putting a square on a skewer. If you rotate that skewer around, that square is not going to look the same until you flip it completely over, which is how many degrees?
180.
That's why it's called a pi bond. So the bond between the p orbitals is a pi bond because it only looks the same if you flip it over, which means a 180-degree rotation. What orbitals combine to make that? We already said 2pz plus 2pz, but a lot of times they just leave the z's out and they just say 2p plus 2p. But this is the second bond that's formed anytime an atom makes a pi bond. You'll always have a sigma bond between the hybrid orbitals, sp2 and sp2, and then a pi bond between the unhybridized p orbitals, in this case, a 2p plus 2p. So I'm going to want you to be able to represent that picture. So let's see what you're going to draw. Okay. Oh, and then finally, the 4 hydrogens then in the C2H4 can bond to these 4 different sp2 orbitals that are pointing on the left and the right. So each of these bonds would each have identical names. What would be the names of each of those bonds?
Or sigma sp2 plus 1s.
That's exactly correct. Does that make sense? This is an sp2 orbital. This is a 1s orbital on a hydrogen. Here's the internuclear axis. When they point at each other and overlap, they're perfectly symmetrical, so it's a sigma bond. So those are all the bonds that exist in that molecule. Is this molecule polar or nonpolar?
Nonpolar.
Oh, you took too long. You should take a nanosecond. Oh, it's a hydrocarbon, nonpolar. Well, you didn't have to analyze anything, okay, just because it's C's and H's. Let's see what you're going to draw now, okay? Let's start with the left carbon. I want you to show me that these sp2 orbitals are trigonal planar. And then you have to show me also the p orbital that's perpendicular to that. So that's why I draw it like this. It's easier in the stick figure picture to draw the trigonal planar array as if it's on an equator. So look at this. I have the sp2 orbital here to the right and the 2 to the left. One is a wedge, one is a dotted line. Can you see that looks like a flat triangle right there? Only we're doing perspective drawing. So it looks like it's on the equator of the Earth. I do that so it's really easy to show perpendicular to that is the p orbital whose lobe points up and points down, and I draw the lobes just as straight lines up and down. This is how I'm going to want you to draw an sp2 hybridized atom. If you go to handout 4 and look at how I have a stick figure drawing for an sp2 hybridized atom, this is it. Okay, so it's listed on there how you need to do that. Let's try to do the same thing for the other atom. It's also sp2. I can't draw it exactly the same because I wouldn't have orbitals pointing at each other. So much like this one was rotated around from this one, just like the mirror image, I'm going to do the same thing down here. Look at that. I've drawn sp2 hybridization with the 3 sp2 orbitals trigonal planar, but I flipped it around so I can have 2 orbitals pointing at each other in order to make a bond. Okay. Those two bonds, orbitals pointing each other, make the sigma sp2 plus sp2 bond. So you see a single bond now between the carbons. How are you making the second bond of the double bond? Well, you overlap the p orbitals on the top and the p orbitals on the bottom. What I'm not going to do is I'm not going to draw a solid line here and a solid line there, because then you'd see one solid line, two solid lines, three solid lines, and that might confuse people to think it's a triple bond, which it's not. This is one bond, and then this is going to be the second bond. So to indicate that the top overlap and the bottom overlap combine to make the second bond, I'm going to draw it as dotted lines like this. So this says you have one bond between the two carbons that's a sigma bond here, and then this whole system here, the overlap of the p orbitals slightly on the top and slightly on the bottom, constitutes the second bond, and that's how all double bonds are created. It's the direct overlap of a pair of hybrid orbitals with the indirect overlap of parallel p orbitals to make a pi bond. Every double bond in the universe happens like that. Okay? That makes sense what we did? Okay, if you like that, you'll really like this. Okay? Now, what if two carbon atoms have a triple bond between them? If they do, we still use the same prefix to indicate the number of carbons, but the ending gets switched to YNE, which is pronounced like a long I, eine. And so this indicates that there's a triple bond between the two carbon atoms. Now, what constitutes a triple bond? A triple bond is always a sigma bond, where a pair of hybrid orbitals overlap directly, and then two pi bonds, and we'll show you an example of how this actually happens. So a triple bond consists of one sigma bond and then two pi bonds. And we're going to look at this with the simplest of the hydrocarbons. It's going to be ethane. And then once again, how many electrons should ethane have? Ethane's formula is C2H2. That should be 4 plus 4 plus 2 more is 10. Curses, I wrote 8 here. What was I doing? Okay, let's try that instead. So ethane has this formula, which has 10 valence electrons, 4 plus 4 plus 2. If we draw the skeletal structure, we draw the two carbons bonded to each other, and the hydrogens are going to be bonded, symmetrically arranged, one on the first carbon, one on the second carbon, like this. That skeletal structure uses 2, 4, 6 electrons, so I've got to put the remaining 4 electrons in as lone pairs, and I try to complete the octet on one atom first before I go to the next. So I'm going to go 8, 10, and I'm done. When I've done that, the carbon that I put the electrons on has an octet. The hydrogens have duets, but the second carbon does not have an octet, so this is not the correct structure. So you'll have to make a double bond by moving a lone pair and making it share, but that's not quite an octet yet. So move the other lone pair and make it share, and there you go. Now you have the correct structure for ethane. Ethane and ethene, the ones with triple bonds and double bonds, are unsaturated hydrocarbons, where ethane, the one with only a single bond, was a saturated hydrocarbon. When they use the word saturated and unsaturated, they're talking about how many hydrogens can you bond to a given number of carbons. These two carbons in this molecule bonded to 2 hydrogens. In the molecule before that had a double bond, the 2 carbons bonded to how many hydrogens?
1 each.
No, because the formula of the previous molecule was not C2H2. What was the formula of the previous molecule?
Oh, the previous one. C2H4.
So if you make a triple bond, like in this one, 2 carbons can only bond to 2 hydrogens altogether. If you make a double bond, 2 hydrogens can bond to 2 carbons can bond to 4 hydrogens. But if you make a single bond between the carbon, like the very first molecule that we did, how many hydrogens could bond to 2 carbons and have a single bond? Go back and find the formula for that molecule.
Three?
It wasn't. The formula wasn't C2H3. What was the formula when we had a single bond between the 2 carbons?
Oh, C2H6, so 6.
So when you have two carbons, the maximum number of hydrogens you can bond to those two carbons is 6. That only happens when you make a single bond between the carbons. That's called a saturated hydrocarbon because you have the maximum amount of hydrogens bonded to two carbons. As soon as you make a double bond or triple bond, can you see what happens to the number of hydrogens that you can bond to the carbons? Gets reduced, right? So it's not saturated, it's not full, it's called unsaturated. You've heard of unsaturated fats before? You know what that is? That's long chains of carbons that have double bonds or triple bonds. You've heard of saturated fats. You know what those are? Long chains of carbon that have only single bonds. That's what it's referring to. Now, in this molecule, the carbons have steric numbers of 2. That means their hybridizations have to be sp. You only have to hybridize one s orbital and one p orbital. Now, what's the arrangement of sp hybridized orbitals? They're linear because steric number of 2 is linear. So I'm going to draw an sp orbital to the left and an sp orbital to the right for both carbons. And because I'm only hybridizing one of the p orbitals, there should be 2 other p orbitals left over in my outer shell of the carbon, one on the y-axis, one on the z-axis. So let's take a look at the picture. In yellow and red, pointing directly to the left and right, are your 2 hybridized sp orbitals. But what's left over in the outer shell of the atom, a pz orbital in purple pointing up and down on the z-axis, and a py orbital pointing towards you and away from you on the y-axis that I have in orange here. Every single one of these orbitals gets a single electron, so they're actually all capable of bonding. Both carbons are sp hybridized, so I'm going to draw my second carbon atom exactly the same. And in this case, I can draw it exactly the same as if I want, because if I do, I'm going to have 2 orbitals pointing at each other. So this one naturally works out that you can actually have them pointing at each other, or if you really want, you can spin it around, but it really doesn't matter. So if I draw them the same and I push them together, you're going to get an overlap between the red orbitals on the 2 atoms. Those red orbitals, remember, were the sps. And so you're going to get a bond, and the name of this bond is going to be sigma sp plus sp. That makes sense? That's one bond. Can you see where the second bond is going to come from? What colored orbitals will make a second bond between these atoms?
Purple.
2B's.
Right. And are they going to make a sigma bond?
No, they're going to make a pi bond.
Right, because the p orbitals are not pointing at each other. If they're parallel to each other as they are, that's where you make a pi bond. So they slightly overlap on the top and the bottom, and that's producing a pi bond. So we'd say pi 2p plus 2p, or if you want to be more specific, 2pz plus 2pz. So that's 2 bonds. Can you see where the third bond is coming from?
The orange
The
one?
orange ones?
And it's just like the purple ones, only it's rotated 90 degrees towards you. It's going to overlap a little bit in front of your picture and a little bit behind, and that's going to be a pi 2py plus 2py. That's why a triple bond is always a sigma bond and then 2 pi's. One pi bond on the z axis and another pi bond on the y axis, okay? And then you have the 2 yellow orbitals left over, so those can bond the remaining 2 hydrogens. What's going to be the name of the 2 bonds here between the hydrogens and the carbons?
Sigma sp plus 1s.
There you go. Now you've named all the bonds in this molecule. Okay. Is this molecule polar or non-polar?
Non-polar.
Perfect. Now let's see if we can draw a picture of this that's not quite as complex as what I have up there in the white box, okay? So for each sp hybridized atom in stick figure form, you're going to draw the sp orbitals on the x-axis, one to the left, one to the right. But you have to show me the purple and orange 2p unhybridized orbitals as well. So here's how we do it. sp orbital to the right, sp orbital to the left. This p orbital is double lobed, so it's going up and down. Draw a line up and a line down. That's going to represent the p orbital on the z-axis. You see the orange one? This is coming out towards you and going back behind you, so you have to draw that 3-dimensionally. The front half of the p orbital is a wedge. The back half of the p orbital is a dotted line, okay? If you look on handout 4, and it shows you how you are to draw sp hybridized orbitals, it'll show you the sp orbitals are drawn linearly, and then it has the unhybridized pz like this, and the unhybridized py like that. My second carbon atom can be drawn the exact same way because there's going to be two orbitals pointing at each other to bond. So I'm going to draw my second one exactly the same, only attach the hydrogen to the very right. And the overlap of those two lines in the middle make the sigma sp plus sp bond. That's one bond. One of the pi bonds will be the overlap of the p orbitals on the plane of the paper, which we draw as dotted lines on the top and the bottom. So that's a second bond. And then you have to overlap the p orbitals in front and behind. So you do dotted lines in front and behind. That's a third bond. That's your picture of this particular molecule. Okay. So when you're accurately drawing pictures of the geometry of molecules, you're really showing all the orbitals in the valence shell of each of those atoms. So these pictures are called Bond-Orbital-Models because you're showing geometrically where the orbitals are on the carbon and the hydrogen and how those orbitals are being used to bond.
So Professor,
Yes.
when we bond triple bonds between carbons, do we not flip it the image 180 degrees?
You
then?
didn't have to, because naturally, if you just draw an sp hybridized atoms, you always have a bond, an orbital pointing to the left and an orbital pointing to the right, so they can actually just exactly line up with each other, right? If you see this, see how this is drawn? It has one pointing left and pointing right.
Yeah.
If I draw another one here, I'll have one pointing left and right. Oh, all you need is one pointing directly at that one. So I just drew it the same way. You can imagine it being flipped 180 degrees perfectly fine, but in all reality, I just drew the same picture twice in a row. I just stuck the hydrogen on the right side instead of the left side.
Okay. Yeah, that makes more sense.
Sure, no problem. So these structures are called bond-orbital models, and this is what your next homework assignment will be due on Monday will be doing. You're going to be drawing geometric diagrams of the bonding in molecules. And so what did we do to try to draw a good bond-orbital model? We did essentially 3 steps. So to draw a bond-orbital model for a molecule, you have to first draw the Lewis structure. You have to predict the hybridizations of each atom. Then when you've done that, you're going to need to then draw the pictures of each of those hybridized atoms. So you have to know how that works. And so on the class website, and that's why I think handout 4 is going to be really relevant to you, when you go to the second page of handout 4, it has the bloopy pictures of each of the hybridized orbitals that we've been drawing in our white boxes here on the notes. And then right next to that, it has the stick figure drawings for each of those. So you might need to refer to that for a while until you eventually, I think, have that set and you can remember it. So you're going to draw the correct geometries for the hybrid atomic orbitals of each atom as shown on handout 4. And you always want to start with the atoms that are involved in double or triple bonding because those are the most complex ones to draw. So if I can give you any hint at all, that would actually be it. Then once you've drawn the correct geometries for all the atoms, you sort of push them together and have them have orbitals overlap to make their bonding. So you have the atoms bond by overlapping their atomic orbitals. And then to make a complete bond orbital model, you're actually going to label each bond. You're going to tell me the name of each bond. And if you've done that, then you have a bond orbital model description of the bonding in a molecule. So let's see if we can try this on a complex molecule or two before we're done today. So let's say we're going to try to draw the bond orbital model for this hydrocarbon, CH3, CH, CH2. Now, you could give the formula for this compound as C3H6, but when they write it like this, they're doing it to your advantage. This is so the organic chemist can look at this and go, oh, the first carbon has 3 hydrogens bonded to it. The second carbon has 1 hydrogen bond to it. The third carbon has 2 hydrogens bonded to it. It tells you how to draw the skeletal structure. So I'll expect you to realize that. So first, let's get the total valence electrons, 4, 4, 4, and 6. That should be 4, 4, 4 is 12, and 6 is 18 valence electrons. I did this one correctly. Now the skeletal structure. Here's how you read this formula. The first carbon has 3 hydrogens bond to it. Then the carbons all bond in a chain. So it's got to be carbon to carbon to carbon. That's going to be bonded to the next carbon, but the next carbon only has one hydrogen on it. Bink, like that. Then that's going to be bonded to the third carbon, and that third carbon has two hydrogens on it. So the formula is telling you exactly the structural way to draw it. How many electrons? 2, 4, 6, 8, 10, 12, 14, 16. We need 2 more electrons. Make one of the carbons have an octet with a lone pair. Bink, like that. And that carbon has an octet, but unfortunately the middle carbon doesn't. So that means you're going to have to move that lone pair into a sharing position and make a double bond. And now everything has an octet configuration. So first step, draw the correct Lewis structure. Use this now to determine the hybridizations. The very first carbon, carbon number 1 on the very left, has a steric number of 4. Because that has a steric number of 4, it's going to be sp3. So when you draw that, you're going to draw its orbitals as a tetrahedron. Carbon number 2 has a steric number of 3. That means it's going to be sp2 hybridized. You're going to draw its orbitals trigonal planar. Carbon number 3 is sp2. You're going to draw its orbitals trigonal planar because it's a steric number of 3 as well. And out of these 3 carbon atoms, I would not start with carbon number 1. I would start with carbon number 2 because it's involved in a double bond. You want to draw carbons 2 and 3 on your paper first. So let me start with the yellow carbon there. That's an sp2 hybridized atom. What does that look like? Trigonal planar geometry. So you want to draw the trigonal planar array on the Earth's equator with the unhybridized p orbital pointing towards the north and the south pole. It's going to look like this. So this is the yellow carbon now. It has sp2, 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 and then the unhybridized p orbital pointing up and down like this. Okay. Now it's making a double bond with carbon atom number 3. So I'm going to draw carbon atom number 3 next. And this is where you really have to rotate this around because you need to have the carbon number 3 with an orbital pointing at it like this. So I draw it exactly the same, but rotate it 180 degrees so the 2 orbitals can point at each other in order to overlap. Okay. Now, those 2 carbons are supposed to be making a double bond. We've made one bond between them. What's the second bond? It's the overlap of those parallel p orbitals like this. There's the double bond between carbon 2 and carbon 3. Once you have the multiple bond drawn, then you're going to just put the rest of the atoms into the structure as best you can. So carbon number 2 is going to be bonded to carbon number 1. I can put it in any one of those spots, right? Carbon number 2 is bonded to carbon 1 and a hydrogen. So I'm going to put carbon 1 here and a hydrogen there. Okay. What's going to go in these 2 spots here? That's carbon number 3. It's bonded to 2 hydrogens. So you're going to bond 2 hydrogens to that. So what I do is I put carbon number 1 in one of the spots, and I try to draw its orbitals as a tetrahedron. Now, we have to go over this a few times before you realize this, but the carbon you're drawing here is not flat on the paper. It's on a wedge, which means it's in front of the paper. And whenever an atom is in front or behind of the paper, it's really hard for you to draw a perspective drawing. I will not expect a perfect tetrahedron if the atom is in front of the paper or behind the paper. So if you notice there, I just tried to make my carbon look like it had 4 orbitals that are about 109 degrees apart from each other, but it's actually not the exact structure we usually draw for tetrahedrons because it's not flat on the paper. So if there's anything going to be lenient in this whole unit, it's going to be drawing tetrahedrons that are on atoms that are in front of the paper or behind the paper. Just do the best you can. But you see that carbon does have 3 extra orbitals. That's going to hold the 3 final hydrogens. So we can bond the 2 hydrogens to carbon number 3 and the 2 remaining orbitals. Carbon number 2 has 1 remaining orbital and it has 1 hydrogen. So you put the hydrogen there. And then carbon number 1 has 3 extra orbitals and the formula has 3 hydrogens. You put the 3 here. That would be your bond orbital model for this particular hydrocarbon. Now, let's see if we can name the bonds. What bonds are between carbons 2 and 3? We have this, which is a sigma bond, and this, which is a pi bond. So what's the name of the sigma bond here? What 2 orbitals are overlapping? Think back to their hybridizations. That sigma bond would be what?
Sigma sp2 plus sp2.
Perfect. And then the p orbitals that are overlapping to make the pi bond would be pi 2p plus 2p. So those are the bonds that exist between carbon 2 and carbon 3. Okay. Now, there are hydrogens bonded to carbon 2 right here, and there are hydrogens bonded to carbon 3. They're here. Those 3 bonds all have the exact same name. They would be the overlap of a 1s orbital from the hydrogen with an sp2 orbital from these sp2 carbons. So they would be sigma sp2 plus 1s. Then the carbon 1 to carbon 2 bond is slightly different than the carbon 2 to carbon 3 bond. It's only a sigma bond. What 2 orbitals are combining to make this wedge here, which is the bond between these 2? What's the hybridization?
SP2.
Say it again.
SP or sigma sp3 plus sp2.
Does that make sense? If you could see that, then you're visualizing what's going on here. That's perfect. It's an sp3 orbital from the first carbon overlapping with an sp2 orbital from the second carbon. Perfect. And then finally, what are the bonds between carbon 1 and each of its hydrogens? What would be the name of those bonds?
Sigma sp3 plus 1s.
1s.
Yes, they would. And that's how you draw bond orbital models. Okay. We have reached the end of the period, so probably what I'll do is I'll probably video record just the last page of this. So if you want to come back later and look at that, but I don't want to keep you past your time because it's almost 8:49 now. So we're going to end at this point. Any then questions on what we've done so far today?
Professor, could you go back to that slide with the 3 steps for the last thing that we just did, I guess, before the CH3, CH2? I just missed the definition or the 3 steps.
I don't know. Let's see. Can I do that?
I don't know. It was just a couple of slides back.
I don't know if I can get to that right now. This might take a...
No big deal. We'll do it later.
Yeah, I'll try to get it to you later if that's okay. Okay. Otherwise, we'll see the other half of the group this afternoon. Today at 2 o'clock is when the pre-lab for experiment 7B is due. So if you want that point, make sure you get that done by 2 o'clock. And then group A will be working on experiment 7B. And then group B will be at school doing experiment 2. We'll see you this afternoon at 3 o'clock.
3 o'clock?
Right, 3 o'clock for lab. Isn't that today for us? Oh, no, not you. Oh, wrong class. Forget it. Timeout. I lied, all that stuff. So tomorrow morning, I'll see group B at 7:30. And then the pre-lab for experiment 7B is due at 6:30 by tomorrow morning. So you probably want to get it done sometime today. So to get that point, make sure you do 7B at before 6:30 a.m. tomorrow. Otherwise, I'll see the other half of you tomorrow at 7:30 a.m., not today, at 3 o'clock. That's better.
Thank you, Professor.
See you later.
It was due at 6 p.m., Professor, tomorrow.
The homework will be due at 6 p.m. The pre-lab is due at 6:30 a.m. before your lab. So look on the schedule. Pre-lab, the OWL pre-lab assignment is due an hour before.
Oh, the OWL. Yeah.
That's what I was talking about.
Yeah.
It's okay?
Thank you. I'll see you at the office hour today, Professor.
See you then, you bet.
Yep. Thank you.
Our last example will be to draw a bond orbital model for CH2CCH2. And once again, the way the formula is written is it tells you the number of hydrogens bonded to each of the carbons. This means 2 hydrogens are bonded to the first carbon, no hydrogens are bonded to the second carbon, 2 hydrogens are bonded to the third carbon. To add up the total number of valence electrons, 3 carbons would make 12, the 4 hydrogens would make 4 more, there'd be 16 valence electrons for this molecule. The first carbon has 2 hydrogens bonded to it. Carbons are all bond row, so the first carbon will be bonded to the second carbon, but the second carbon does not have any hydrogens on it. And then that second carbon is bonded to the third carbon, and that third carbon has 2 hydrogens bonded to it. So the skeletal structure looks like this. This is using 12 electrons. We have to add 4 more. So after these 12, 13, 14, 15, 16, we make octets on the outer atoms first, which we've done. So the outer carbons have octets, but the central carbon does not. So we have to move lone pairs into sharing positions to try to make the central carbon have an octet. This lone pair can be moved to make a double bond, and this lone pair can be moved to make a double bond. And now all the carbons have octet configurations. The steric number for the first carbon is 3, so therefore its hybridization is sp2. The second carbon's steric number is only 2, its hybridization is sp. And the last carbon's hybridization is sp2 because its steric number is 3, just like the first one. So if we're going to draw the bond orbital model for this, we have 2 multiple bonds. You can start with either one. So what I'm going to do is I'm going to start with carbon number 1 and draw its sp2 hybridized orbitals exactly like the last one. We have our 3 sp2 orbitals drawn in a trigonal planar geometry with the unhybridized p orbital up and down. But now when I draw carbon number 2, this is going to be an sp hybridized atom. So from handout 4, and from what we talked about today, sp orbitals are linear. They should be pointing left and right along the x-axis. You should have a pz orbital pointing straight up and down, and a py orbital pointing towards you and going back behind the plane of the paper. It's going to look like this. So we've drawn a sp orbital to the left, an sp orbital to the right. This is the pz. This is the py. Okay? And the way these two are going to bond to make a double bond is by overlapping their pz orbitals like this. Now, this particular molecule is kind of rare. It has 2 double bonds in a row, and I want you to notice what happens when you have 2 double bonds in a row. I'm going to need to draw an sp2 hybridized atom to the right. If I draw it exactly like the one on the left, except for the mirror image, I'm going to have my p orbital on the plane of the paper. Unfortunately, this p orbital is already being used. It cannot be used to make a pi bond to the first atom. Where's the p orbital on this middle atom that's open? It's pointing out towards you and going back. That means for the third atom, the p orbital cannot be on the plane of the paper. You have to rotate that entire atom 90 degrees towards you, so its p orbital is pointing directly at you. And we had done this when we first introduced sp2 hybridization a couple of days ago. When you rotate it 90 degrees towards you, the equatorial positions here that are on the Earth's equator, when you tilt it towards you 90 degrees, now all of a sudden are flat on the paper. And so this picture is going to wind up looking like this. The sp2 hybrid orbitals are now all flat on the paper instead of being on the equator. And the p orbital, instead of being up and down, is tilted 90 degrees for you, so you draw it coming out and going back. We have to do that so that the p orbital on carbon number 3 can be parallel with the p orbital on carbon number 2. And look at this. There's your pi bond. That's a pi bond that's 90 degrees rotated from the pi bond between the first 2 carbon atoms. Anytime you make 2 double bonds in a row, the pi bonds have to be rotated 90 degrees. So 2 more hydrogens are going to go on this last carbon here. This will be the bond orbital model for this particular molecule. If we want to name each of the bonds, the carbon-carbon bonds are always the overlap of an sp2 orbital on the outer atom with an sp orbital on the inner atom. sp2 on the outer atom with an sp on the inner atom. So those are sigma, sp2 plus sp. And they also have a pi bond. It's a pi 2p plus 2p. The first one you can be more specific and say pi 2pz plus 2pz if you want. This one you can say pi 2py plus 2py if you want to be more specific. All the carbon-hydrogen bonds are the same. Those are going to be the overlaps of 1s orbitals from the hydrogen with sp2 orbitals from the carbons. Those are going to be sigma, sp2 plus 1s.